Okay, class. Yeah. Okay, so we're done with the first part. First part is what? What we talked last class? Binding energy. Before binding energy, we talk about mass defect. Okay, and before mass defect, we talk about E equals mc squared. So what is meant by E equals mc squared? According to Einstein, mass and energy are they actually the same object. Actually, they are same entity. A different form. They are in a different form. Mass can convert to energy. Energy can convert to mass. So energy can create mass. Okay. A new idea. All Einstein said is something people will think like a fairy tale story, but looks like correct later. Okay. Okay. So, some of you ask me, so is that means conservation of energy cannot be applied here? Yes, you can't apply conservation of energy. What is conservation of energy said? The energy cannot be destroyed or created, only can transform from one shape to another, right? One type to another. That only works for macroscopic level, big body. When it comes to the nuclear stage, that rule has been violated. Okay, so you don't talk about conservation of energy in nuclear stage. Nuclear stage, don't know what happened. Mass has been destroyed, turned to become energy. Energy create mass. That things happens. That's why a new conservation has been found. What is that? Mass energy is together is conserved. Mass energy together is conserved. Okay. So mass is conserved? No. Energy is conserved? No. For a microscopic level. For a big body, yes. Okay. Mass is conserved, energy is conserved. Okay. So today what we're going to talk about is half-life, decay. Okay. You never do fission and fusion, you leave unstable nuclei, it start to decay. Transformation will happen. Uranium, you leave it also, it try to achieve stability, okay, by decaying. Okay, so what is radioactive decay? As you learn, right? What is radioactive decay? It's a spontaneous and a random disintegration by heavy unstable nucleus into more stable product through the emission of radiation such as alpha, beta, and gamma. Okay, radioactive decay is a process experienced by, it's a type of spontaneous and random. I think I stressed this last class, I mean in AS last time. What is meant by random? We don't know how many going to disintegrate at a particular time. It's totally unpredictable. You can't predict which atom going to disintegrate. Let's say you have 1 kg of uranium. Maybe the first 1 second, the top 10,000 nucleus will disintegrate. After second, maybe none disintegrate. The third second maybe some inside 4,000 disintegrate, another 2,000 on top disintegrate. So it's totally random. It's unpredictable. Okay. And it's spontaneous. So why spontaneous means? What is spontaneous means? Unaffected by external factors. We cannot control it. Okay. It is independent of pressure and temperature. You rise pressure, you rise temperature. Don't think the radiation is going to go up. Never change. Okay. So who experience radiative decay? Unstable nucleus. What is the purpose? To become stable by giving out radiation. Okay. So the instrument we use to detect radiation is the GM tube. You learn in your O level. Geiger-Müller tube. Geiger-Müller tube contains argon gas, if I'm not mistaken. And radiation get into the argon gas. Argon is what? Inert gas, right? Group 18. Group 8 or group 18? You learn group 8 or group 18. Your periodic table. Group 18. Group 18. Okay, so group 18, argon is there. So we know the arrangement is so perfect. But you send alpha radiation into the GM tube, which contains argon gas. The argon gas electron will be removed, ionized, and the ionization causes a current flow in the tube. Okay, because the center wire and the body of the tube different voltage, different polarity. Maybe the body is negatively charged. Inside there is one wire inside which is positively charged. The ionized argon will move. The electron move one side. The nucleus will move another side. Produces a reading, count reading. Okay, so the count reading GM tube is connected to a rate meter. A rate meter is the one counting how many atoms of argon has been ionized. Okay, so if the reading is 10,000, then we assume that 10,000 argon atom has been ionized. Okay, so if the ionization of argon atom is a lot, that means we say radiation is a lot. So GM tube. So Geiger-Müller tube with the rate meter is connected. The radiation detector can be registered about 20 to 50 per second. The amount of reading. I think you learn about background count rate, right? Background reading. Okay. So in this room, you put a GM tube also, you have a reading. This is called background reading. What causes of background reading? Anyone? What causes the background radiation? The source of background radiation? Yeah? Anyone? The cosmic ray. The main one is what? The radon gas from the underground. Radon gas. Major, I think more than 50% of the background radiation, I think, because of the radon gas. Yes, I told you about that, right? Radon gas, cosmic ray, and stones here. Some of them may be a small dust, maybe radioactive, contribute to the radiation. So you have a background radiation. It comes from low intensity radiation from small quantity of radioisotope found in the ground, atmosphere, and cosmic rays driving surface of the Earth. Okay. In exam, they might ask what is the source of background radiation. So cosmic ray, radon gas, okay, can be the source. Okay, now come to the calculation part. Okay, before we go about this slide, you need to answer this question to me first. Let's say you have 1 gram of uranium. You have 1 kilogram of uranium. You put a GM tube the same distance away from the both source. The reading of the GM tube will be same or different? 1 gram of uranium, 1 kg of uranium. Both are uranium. Put a GM tube. Both reading going to be the same or different? The amount of argon gas ionized, same or different? Different, right? The radiation going to be different. So the big mass will produce a big radiation. Okay, big radiation. So the first formula discovered about radiation is this formula. This formula. Okay, what is this formula? The d and dt is actually called activity. Okay, the rate of decay is activity. decay constant. Decay. D and dt is called activity. Radioactivity. Activity. D and dt. N is what? Number of particles. T is what? Time taken for that n particle to decay. Okay. If 10,000 nucleus decay per second, so d and dt is 10,000. Okay. So yeah, if d and dt big means the radiation we see is radioactivity is big. Okay. So first formula they discovered is the activity is directly proportional to n. This is the first formula. The activity is found to be directly proportional to n. Bigger the number of atom, more greater the activity. So yeah, d and dt is the A. I can represent it as A proportional to n. Actually negative because it's a decay. The activity is always going to drop. It's a decay, a drop. The dn, right? The n final minus n initial going to be always negative, right? Final n going to be smaller than the initial n because it's decay one. Okay, the number of uranium dropping. Okay, that's why here the sign negative was placed. Negative shows decay. Okay, but in your Cambridge, they will say as they consider it as a decay constant, as a decay. Therefore, in Cambridge, they ignore the negative. They just put A proportional to n. And mathematically, A, when you equate, you bring what? A constant, right? So in this case, they put lambda n. So this formula, d and dt is as A equals to negative lambda n. This is the actual formula, negative because it's a decay. But Cambridge never use as negative. They ignore the negative. They just put A equals to lambda n only. So ignore the negative. A equals to lambda n only. This is the first formula. What is A stands for? Activity. What is lambda? Lambda called decay constant. Lambda got special name called decay constant. Okay, decay constant. And n called the number of atom available, the initial number of atom available. Okay, so how they got A equals lambda n? From the understanding that A proportional to n. A greater n means greater activity. Okay, now the storyline is more about the decay constant. Okay, decay constant. Okay, what is the definition of decay constant? It's written there. Decay constant is lambda is a fraction of total number of atoms that decay per unit time. There is another one better definition. Please write this. Decay constant is the probability. Decay constant is the probability for a nucleus or for an atom. Probability for an atom to decay per unit time. What is decay constant? Is the probability. It's a probability. Decay constant is the probability for an atom to decay per unit time. Okay, what is decay constant? The keyword is probability. Decay constant is the probability for an atom to decay per unit time at that particular time. That's decay constant. Probability. What is the maximum value of probability will be? What is the maximum probability? 1. So decay always less than 1. So let's say you have two substances, substance 1, substance 2. Substance 1 as a decay of 0.5, substance 2 as a decay constant of 0.7. Lambda 1 is 0.5, lambda 2 is 0.7. Lambda 1, substance 2, which one is more unstable? Lambda 1 or lambda 1 is 0.5, lambda 2 is 0.7. What is meant by 0.5 lambda? That means probability for an atom to decay per unit time is 50%. 0.5 is 50% one. So one substance got 0.5 lambda, another substance 0.7 lambda. So which is more unstable? 0.7 is more unstable. So conclusion, more greater the lambda means that element is more unstable. Okay. So greater the lambda, greater the instabilities. It's not really stable. And the lambda is constant for a substance, never change. Uranium has a fixed lambda. Carbon has its own fixed lambda. Okay. Okay. So the lambda unit is per second. Per second, you can add more. Per second, per minute, per hour, can be anything. Okay. But SI unit is what? Per second. Another biggest trap, whenever you use this formula, whenever you use A equals to lambda n, lambda is, you must put it as per second. You put it per hour, wrong. Okay, must put per second. If you put lambda as per second, the activity unit will be formed into a standard SI unit for activity called Becquerel, the new unit. Okay, let me shift for a while. This is the unit for activity, Becquerel. A equals to lambda n. The A is the unit for activities Becquerel. But in reality, got lots of unit for radiation. This is the standard unit Becquerel. Okay, like kilogram, gram for mass, ton. Kilogram is SI unit. Radiation, Becquerel is the SI unit. Okay, 1 Becquerel. So what is meant by, okay, before we go to the unit, so yeah, go back first. So conclusion is A equals lambda n put per second. Let's say they give 0.1 per minute. How do you convert to per second? So you know la conversion. 0.1 per minute. Per second, the number will get bigger or smaller. Probability for decay per minute is 0.1. Probability to decay per second, the probability is even smaller, right? So divide by 60. Divide by 60. So try to understand the conversion. Sometimes they give per year also. So per minute to per second, you divide by 60. Divide by 60. Yeah. Per hour to second, then you should know 365 days, 24 times 60 times 60. Lots of calculation to convert it to second. Okay, A equals lambda n, lambda must be per second. Okay, I'm stressing many times because lots of past year, this is the problem. They never convert. Student forgot to convert. All gone. Okay, so that's the first equation. Okay, we have 3 equations under radioactivity. First equation is A equals lambda n. Second equation, first equation is very low profile, sometimes comes up. The most dominant one, very useful, is the second one. This is the second equation. Very useful, most of the time will be used in your calculation. This is the formula. N equals to N naught E negative lambda T. This is the derivation. In exam, they won't ask derivation. Actually, what you need to know, the N equals to N naught E negative lambda T actually formed from A equals to negative lambda T, the activity formula. The A equals to negative lambda, actually it's negative, as I told you, negative. So you know the dt to bring the other side, N is down, integration involved, at the end you form this formula. Okay, your maths you learn integration, differentiation, right? Try to understand this derivation. Okay, so I more to how to use this formula. Okay, this formula, try to understand the second formula. And what is this N? This N is the number of atoms still remain after time t. Still remain. This one then is still remain. Still remain after time t. Okay, uranium maybe 1 kilogram. After 1 hour later, it becomes 0.8 kilogram. So N will be how much? The number of atom of the 0.8 kilogram still remaining. Okay, N naught is what? N naught is the original atom and the time 0 when the origin original number of atom. Okay, E negative lambda, lambda is decay constant, time is the duration you want to calculate, the time you want to calculate the n. After 2 hours, you want to find the n. So T is 2 hours. Okay, T. Okay, so n equals to n naught E negative lambda T. This n not only can use for number of atom, it can represent 4 things. It can go for activity. That means can write A equals to A naught E negative lambda T. For activity can n stated. For count rate also we can use this formula, C equals to C naught E negative lambda T. For mass also can, M equals to M naught E negative lambda T. All decreases in the same manner, exponentially drops. And mass of the radioactivity substance drops, its number of atom drops, count rate drops, and activity also drops exponentially. Okay. If the question talk about mass, so you use the mass formula. They talk about initial number of atom is this much. What is the final number of atom after 2 hours later? So you change to n. N equals to n naught E negative lambda T. Sometimes they ask for activity. Original activity is 2000 becquerel. After 2 hours later, what is the new activity? So A equals to A naught E negative lambda T. Okay. But whatever it is, the biggest mistake students do is the value of n. They confuse, is it the still remaining or the one already disintegrated? The one still remaining. Yeah, the one still remaining. Okay. So straight to the point, not much to read, get ideas here, no new ideas. A is A naught E negative lambda T, the unit for activity is becquerel. Becquerel, SI unit. Okay, next. So I believe O levels you learn what? N versus time, the graph going to go down, straight down. This is actually, now you know the formula. The formula is what? N equals to N naught E negative lambda T. Now you know the formula. The decay happens exponentially. What's the formula? N equals to N naught E negative lambda T. Okay. And you know, N naught become half N naught, take first half life. First half life. Half N naught become quarter N naught, take another half life, and so on. Okay, what is the flexibility of doing this formula? Last time, let's say they say one uranium as 1 kilogram. Half-life is 500 years. Let's say 500 years. So after 500 years, how many mass is left? So half kilogram, half of the mass is left, right? So 1 kilogram become half kilogram. Okay, but now they can ask question. Half-life is 500 years. What is the mass left after 400 years? So 400 is just not perfectly one half-life, you know. So in between. So now you can find the mass in between, okay, by using this formula. Just you substitute what? Just substitute the T as the whatever time they require. In this case, let's say I ask for 400 years later. So T you put as 400 years, but the lambda must be in per year. This is another trap. The lambda and T must be always the same unit. Okay, another trap. The Cambridge always try to confuse the students by giving lambda in year and the time in second. So you have to convert one of them to become the same. Okay, if lambda is in per year and time, you try to put in year, you put it in year, then same, then it works. Don't put different unit, wrong. Okay, all gone. So lambda and T same unit for this formula. Okay, so that's the second formula. The last formula is half-life formula. Okay, so nothing new for you. You learned this many times. 4 years, I think, maybe 4 3 years. So what is half-life? Remember the time taken for the number of radioactive nuclide to disintegrate to half of its initial value. Okay, this derivation, this is the third formula for half-life. Now, last time you never know any half-life formula. Now the half-life formula is T half is 0.693 over lambda. Half-life formula. This derivation you have to know. In exam, they say the student must know how to derive the half-life formula. This could be a 2 marks question. Okay, so let's we learn how to derive it. The derivation for half-life formula start with the second formula. N equals to N naught E negative lambda T is used. Okay, when the T is T half half-life, the number of undecayed atom N will be N naught over 2, right? N naught become N naught over 2. So the N we can replace with N naught over 2. Then next, so bring the N naught cancel, so it's become half here. Okay. So do you understand this step from here to here? Maths, so the half become 2 power of -1. Negative power, I think, cancel. So the negative power is not there anymore because the half we make it 2 -1. So -1 is cancelled. So it's actually half is what? E negative lambda T. So it's same as 2 -1 E negative lambda T. So I think negative cancels, so become 2 equals to E lambda T. As shown here. Lambda T apply. Okay, then bring ln both sides. Whenever there is exponential, bring ln both sides. So ln 2. So here the E going to be won't be there anymore. So power get down is lambda T half. So yeah. So half-life is ln 2 over lambda. Okay, ln 2 over lambda. That's the third formula. So first formula is what? A proportional to N, you got A equals to lambda N. First formula. Then by using A equals lambda N, you got N equals to N naught E negative lambda T. Second formula, the most useful one. And the third formula from N equals to N naught, you get the third formula, half-life, ln 2 over lambda. Ln 2 over lambda. Okay. Half-life also intermediate, okay. But the one low profile is A equals lambda N. Okay. When you use third formula, half-life equals ln 2. If lambda you put per year, then the time you get is year. Per year, lambda per year means time will be in year. So lambda and T, try to put the same unit if they involve in the same equation. Okay. So lambda you can put per year, per month, anything can for the second and the third formula, but remember, not for the first formula. First formula, lambda must be always what? Per second. Okay, remember, lambda for the first formula must be always per second. The second and the third formula, lambda you can put per year if you want. And the time also must be in years. But the first formula, lambda always per second. Okay. Okay. So kind of some mathematical arrangement. So N equals to N naught E negative lambda T. You bring the ln to both sides. It's going to be ln N negative lambda T ln N naught. So we plot ln N versus T. It's going to be a straight line. Y equals to mx plus C. So your gradient will be what? Your gradient will be negative lambda. Your gradient will be negative lambda. So linear law. You can ask you to plot. Okay. This is your linear law. Okay. So yeah, so some substance with a different rate of life. So radon is 1 minute. Uranium is 4,500 million years. It's quite big. That's why used in the nuclear reactor. Good radon to have a very short half-life. If radon has a few million years, I think many of us won't survive on this planet because from the ground, a lot of radon gas is coming out. Thank God it's 1 minute. By the time it reaches the surface, I think 1 minute it's just not there anymore. If it's still there, that's why, as I said, building the underground room is like dangerous. You have to check the radon level. Okay. So good. It's only 1 minute. Okay, we are safe. Okay, so now use that 3 formulas. You look at this question. Try to work out. Use one of the formula. Check which one is the best for this question. Okay, what is the 3 formula? E equals to lambda n, first one, n equals to n naught E negative lambda T, second one, and third one is half-life equals to ln 2 over lambda. Okay, use these 3 formulas. So half-life of radium is given. What fraction of radium would remain after 1 times 10 power of 3 years? What fraction of radium would remain? Fraction. That means they are looking for N over N naught. Yeah, N over N naught. More easy, I think. N over N naught you are looking for. So, which formula? Of course, the second one. Okay, I think the second one could be the best. Right? You are looking for, when you read this question, you must remember you are looking for N over N naught. Is what? Okay. Fraction of atom remaining. So yes, so this should be your, this is another way of doing. Yes, we can use N over N naught E negative lambda N. We are looking for N over N naught E negative lambda N, but we stuck, we don't know the lambda. So we need to find the lambda first. That's the working on top. Okay, so remember, if you know half-life, you can find lambda. Like getting period and frequency. You know period, you can find frequency, right? They are linked 1 over half. Same thing. If you know half-life, you can find lambda. They are related. Half-life and lambda is inversely proportional. Half-life is ln 2 over lambda. Okay? So put in your mind. If you know half-life, you can find lambda. If you know lambda, you can find half-life. T half is ln 2 over lambda. Okay. So that's what has been worked out first. Find the lambda, then n equals to n naught E negative lambda T. You are looking for n over n naught. And now be careful here. The lambda and T must be same unit. The T, what unit you put? T is time is in years. Okay, time is years. And half-life also in years, therefore lambda also you get in years. In years. So both years, okay. So you can get the answer. This question a little kind because all same unit years. Okay. So 0.652 still remain. That means how many percent still remain? 65.2% of that element is still remain undecayed. Okay, go to the next one. Okay, this one here. Okay, yeah. You try. This is the 3 formulas again. Okay, A equals to lambda n equals to n naught E negative lambda T, and half-life is ln 2 over lambda. Okay? 1, 2, 3. Oh, this is actually, you don't need to use the formula also if you want, but I prefer you use the formula. Because it's just a multiple of half-life. It seems like your O level or Form 5 level of question. Exactly some multiple of half-life, not the intermediate time. But I still want you to use the formula. So half-life is 30 years. They're asking if the initial number of cesium is 10 to the power of 4. 10 to the power of 4. What is the number of cesium nuclei that have decayed? This is another trap. Which is already decayed. The n is actually the one still remaining. So use the formula, find the remaining. Then don't forget to minus the original with the one remaining to find the one decayed. Okay, be careful. They're asking the one already decayed. There is no formula for the one already decayed. The one left, we have formula. N equals to n naught E negative. So n is the one remain. So find the remain, and later find the decayed one. So which formula likely to be used again? Of course, the second one. Second one. Lambda in 30 years. Lambda is 30. Time you put 90. Yes, 90. So both years good. Same unit. So you find the n. So after you find the n is the one still remain. So n naught minus n will give you the one decay. This should be your working. I want you to adapt the method 2. Method 1, your from O levels or from 5 level. I think I don't use that. You go for method 2. Make use of the equation. It's more versatile. Anytime you can find. Okay, method 2. T half is 30 years. So find the lambda, or here we calculate lambda t. So n equals to n naught E negative lambda t. So find the n naught was given. n naught is 0.125. So 12.5% still remain. Yeah, so 1 minus 0.125 times 10,000 is the one already disintegrated. Okay, so for the another one. Another one, next one. Oh no, hold on. This is okay. We're done with the topic. This is like combination of all the parts. Okay, you can give a try this question with the answer. I don't want to go through this. Okay, I want to go through the past year one question. Okay. Okay, so this is a pass here. The question I want to do the first one. Okay, give a try. The entire knowledge you learn about this topic. First, A. So very common. The first term they're going to ask what is meant by decay constant. Okay, probability for an atom to decay per unit time. You must use it per unit time. Okay, don't just say probability for an atom to decay. Wrong. 1 mark maybe. Probability for an atom to decay per unit time. Okay, next. Say the relationship between activity and N. A equals to lambda N. The lambda is decay constant. We call it decay. Because we say the term decay, we never put negative. Okay. Okay, the question is the one I really need to focus is the C. Okay, come on. This is something new. I haven't done this before. Try to get your chemistry knowledge too. Those who are doing chemistry, I think, should be better understanding. Those who are not taking chemistry, you need to, I think maybe O level you did chemistry. Try to recall back your mole concept. Mole. 1 mole of substance equals to the Avogadro constant number of particles, right? You have to recall that. Mole concept you have to know in physics. Okay, I think this is chemistry, but you have to know. So they're asking how many number of molecules in 1 meter cube of air. They say 0.024 is 1 mole. 1 mole is 0.024 meter cube. 1 divided by 0.024 times with anyone? You want the number of molecules. So you find number of mole, right? Number of mole is 1 meter cube. Check how many mole. 0.024 meter cube is 1 mole. So 1 meter cube is how many mole? 1 divided by 0.024. That's number of moles. But they want molecules. So number of mole multiplied with what? You get Avogadro constant. So you must multiply with Avogadro constant. So yeah, 1 divided by 0.024 times Avogadro constant, get the number of molecules. Okay, let's learn the technique. Okay, second one. The last part for today. The maximum permissible number of radon atoms in 1 meter cube of air. So scroll up. They want what is the maximum number of radon permitted in 1 meter cube of air. Okay, scroll up. So 1 radon permitted for this much of molecule. So how many radon permitted for 1 meter cube of air? So the answer in A1, what do you do? Answer in A1, you know the number of molecule. 1 radon permitted for this much of molecule. So you have A1, C1 is the total molecule you have. So how many radon permitted? The answer in C1, you divide or times with 1.5 times 10 to the power 21. Divide 1.5 times 10 to the power 21 times with 1 atom. One atom. So C1 answer divided by 1.5 times 10 to the power 21 should give you the number of radon gas permitted. Okay. How much you got? 60,000? 16,000. So you can breathe radon gas. There is a permitted level. Your immune system can fight. But even more than that, mutation most likely. Okay, class. So we stop here. The next lesson, practical. I want you to go through these questions, these past years. If you have any question, we do it on Friday. Maybe the first 15 minutes. If you have any questions, give a try. These 2 days. If you don't have, we continue with the new topic. Okay, this Saturday we'll be having extra class again, 10:30. 10:30 12. Yeah?
Is this neutral happened yesterday? Yesterday.
Where?
In a country. Neutral gas.
Nuclear is definitely something in CNS. Maybe the footage is not really correct or what. This nuclear topic will work.
This Saturday,
10 to 12. 10 to 12. So we discuss maybe 1 o'clock.
CNN. CNN.
Oh, CNN.
10, 12 days. I don't know where is it.